Welcome back to your second to last day of new material. This is Physics 235, Week 14, Day 2, scheduled for release on Wednesday, April 22nd, and today we're going to be talking about single-slit diffraction. So, to kind of prep you for what we're going to see today, I have over here on the left the double-slit interference pattern from a few lectures ago. And we had pointed out that there were some extra dark spots at the locations I've labeled with these green arrows here. And today, and a little bit on Friday, we're going to explain those dark spots. So, this interference pattern was a double-slit pattern. And when we did our derivation of the formulas for the double-slit pattern, we found an alternating and evenly spaced, at least when theta is small, series of bright and dark fringes. But we didn't see anything in that original explanation or derivation about these dark spots here. So the dark spots there come from the fact that even our double slits, each of those two individual slits, each one of those has some width itself. And our original derivation assumed that the width of each of the two slits was 0. But in real life, no slit has a width of 0. So the individual slits we were using in the double slit experiment each had some width of their own. And it's this finite width of each slit that is the difference between some of the diagrams from the double slit experiment where we just saw a bunch of evenly spaced bright fringes and something like this diagram over here on the left side of our image that has those extra dark spots. So what we're going to explore today is the diffraction pattern that's caused by a single slit. So we say that a single slit of width A will create what's called a diffraction pattern. It will still be interference that's causing the bright and dark spots that we find, but we're going to call the interference pattern from a single slit by itself a diffraction pattern, and we will reserve interference pattern for the double slit results, the evenly spaced maxima, to make things a little clearer for what will come up on Friday. So let me show you what a single-slit diffraction pattern looks like. So here we have a figure from your book that shows you what the intensity would look like, or the brightness would look like on the screen for a single-slit experiment. Our incoming light is coming in from this side, and our slit has a width of A. So that is this width right here. That is the distance A. And then on a screen some distance that we will later still call D, big D, away, we get an interference pattern. And it's a slightly different interference pattern than what we saw with the double slit. We can see some similarities. Our brightness is largest in the middle and decreases as we move out toward either edge. And we do have alternating bright and dark fringes, but there are a couple differences. We will have what we call a central maxima, which is going to be this bright spot here, measured from the first dark spot on one side to the first dark spot on the other side. And then after that central maxima, we will see that all of our zeros are evenly spaced and will be continued to be evenly spaced until the small angle approximation breakdowns. And the evenly spaced zeros will continue onto the other side of this intensity pattern as well. And that central maximum, you might notice, is a little bit wider than everything else. So the distance from a 0 on one side of the central maximum to the 0 on the other side is going to be twice as big as the separation of any other zeros to the next 0 over. So we can see this same pattern over here on the far left. So ignore the tiny little dots. Those are from the double slit part. But in terms of just the single slit interference pattern here, we have one big central maximum, and then we have evenly spaced bright spots after that. So that's how the diagram here on the left connects to the diagram over on the right. So now I want to work on the mathematics for this. And it will turn out the math is going to work out for the single slit pattern that we're going to be looking for only the locations of dark spots. We're not going to have a formula for the location of light spots. So let's get a figure from your book up here and begin to discuss it. So this is the figure from your book that I want to talk about, and I want to think through this process for each of these scenarios. So you can see that we're going to have two bright fringes here and two dark fringes here. And this is just going through sequentially the bright and dark spots as we get to them. So first, let's talk about image A here that I'm going to talk about in red. We imagine not just one light ray, but many light rays going through this slit right here. And when we're talking about the resulting bright or dark spot on the far wall, we want to again look at our path length difference. So hopefully you can see in part A of this figure that all of our light rays are going to travel the same distance to get to the screen. So our path length difference will be 0, which is a whole number of wavelengths, and this will produce a bright spot on the screen. And the bright spot we get here will be the central maximum, which is directly across from the single slit that we get. Now the next one I want to talk about is this first dark spot right here, and I'm going to do this work in green. So here we have still the same 7 rays all traveling off to the right towards the screen, elevated at some angle theta from completely horizontal in this diagram. And I want to convince you that somehow all of these rays, no matter how many of them we draw, we are going to get complete destructive interference. So this diagram here happens when the overall path length difference from the top ray up here to the bottom ray down here is equal to 1 wavelength. So this distance right here that I've labeled in green is 1 wavelength. So using some other colors here, I want to start to think about these rays. So let's imagine this ray right here up at the top that I'm going to mouse over in orange. This ray travels the shortest distance to get to the spot on the screen that will be dark. But then if we go down here to this other ray that I'm labeling in orange, think about the path length difference between these two rays. We had a path length difference of 1 lambda comparing the very top of this diagram to the very bottom, the topmost ray passing through the slit to the bottommost ray passing through the slit. So if we compare these two orange rays to each other, they'll have a path length difference of half of a wavelength. So let me write this down in orange. Well, but those two rays aren't all of the rays. We've drawn 7. Technically, they're an infinite number. What about the rest of them? Well, we can look at the next ray over. This ray here in yellow is at some length that it has to travel to reach the screen. And like before, for the orange ones, to get from this top orange one to the one that interferes destructively with it, we went down 1, 2, 3 rays. So that means that yellow ray is going to completely destructively interfere with this yellow ray. And we can continue this process. I'm going to skip over green and just go straight to, we'll say, brown. So these two brown rays will also destructively interfere. And so on. If we want to get all the way to the very bottom of this image to see, well, what matches up with this ray here, well, then we're right up against this original second orange ray. So for every ray you can pick in this entire slit of width A, there's a ray that it pairs with that the two rays completely cancel each other out. So what we have here is kind of paired destructive interference. There's not a single ray you can pick in that whole slit width where you can't find one and only one ray that completely destructively interferes with it. So that's why we're getting the dark spot here. And you can see that this dark spot happens when d sine of theta is equal to, or rather, big D sine theta is equal to 1 wavelength, or the path length difference between the top ray and the bottom ray is 1 wavelength. So if we skip over here to part D, which I'm going to do in blue, we're going to have the same type of thing for this second dark spot. And the second dark spot will happen when the path length difference from the very top ray to the very bottom ray is 2 times the wavelength instead. So here we will still have paired destructive interference, but in a slightly different way. So if we think about it first, this top ray up here that I'm mousing over in orange, to find the ray that completely destructively interferes with this orange ray, we need the ray that has a path length difference of half of a wavelength from the one we've drawn. And that is actually this second ray right here. So then we could kind of continue along and say, well, some space a little further over from this first ray, there'll be a ray I'll label in yellow, and that will completely destructively interfere with this other ray that I've drawn in yellow. And then using green as my next color, this ray right here in green will completely destructively interfere with this ray in green. So at least for the top half of the slit, we still have that paired destructive interference where each ray has a sibling that completely cancels it out. And then we could do the same thing for the bottom half of this image, or for the bottom half of the slit. This ray in purple will cancel out with this ray in purple. And then this ray in brown will cancel out with this ray in brown. And this ray in pink will cancel out with this ray in pink. So again, every ray has a pair that cancels it out, and we get a dark spot. So what might this look like when we're talking about a bright spot? The bright spot in the beginning, the central maximum, was pretty trivial to think about because all of the rays traveled the same distance. And it was kind of easy, or we're at least learning how to make it easy, to explain the dark spots where we have destructive interference. Because all we need to do there is find a pair for every ray that cancels it out. But what about for a bright spot? So this will be the first bright spot after the central maximum. So let's try to go through our same process of pairing the different rays here. So if we take this top ray first that I'm going to color in red, then the ray that will cancel this out is the ray that has a path length difference of half of a wavelength from the original ray I just drew in red. So that is this ray right here. So these two red rays cancel each other out. And this ray right here in orange will cancel out with this ray here in orange. And this ray here in yellow will cancel out with this ray here in yellow. So that means everything from the very top of the slit all the way down to here. All of this cancels out. But now we go to our next ray and say, well, what about this one here? Well, we could say, well, that cancels out with the ray at the very, very, very bottom of the slit. But now, what about this blue ray? What about this purple ray? The blue ray and the purple ray in this diagram don't have a pair to cancel them out. So not all of our rays pair off and cancel each other out. We have some rays that are flying solo and have nothing to cancel them out, and it's those rays that are responsible for creating a bright spot here. And our bright spot here is going to be dimmer than the central maximum. Hopefully that makes some sense, because in our first diagram over here on the left, none of our rays had pairs that canceled each other out. So it's the light that travels through the entire slit is all constructively interfering. But when we looked at our first bright spot after the central maximum, all of these rays that I bracketed in red, these all cancel each other out. So it's only as bright as the light that makes it through this bottom third of the slit is. So we don't have as much light getting through. It's not the entire slit width's worth of light. It's just a third of the slit width's worth of light. So that should convince us that this maximum that we get should be dimmer, and it is based on the diagrams I showed you on the previous pages. So the easy formulas here will come from the dark fringes. So here, in our first dark fringe, we have that sine of theta is equal to 1 of the wavelengths divided by big D, the distance to the screen. And then for our second dark fringe, we have sine of theta is equal to 2 lambda over D, the distance to the screen again. So we're going to get a single equation here, but it's only going to tell us where our dark spots are. And we'll just have to remember that the bright spots are kind of evenly spaced amongst those dark spots. So for single-slit diffraction, we're going to have dark spots where A sine theta equals m times the wavelength, where m is an integer, but m cannot be 0. We do not have a dark spot right at the center where theta equals 0. That's the central bright spot. So we have here a diagram from your book, and just to kind of connect this to the diagram with bright lines we've seen, the higher the intensity graph is, the brighter the line. So we'll have our central maxima right here, and if we take all these zeros and extend them up so we can draw our diagram as precisely as possible here, we'll have our central maximum here in the center with a dark spot along the dotted lines, and then we will have our additional bright spots, evenly spaced as long as the small angle approximation holds, spreading out. So at this first dark spot right here, we have that sine of theta equals lambda over A. So if we plug this into our equation above, we would have then A times sine of theta, which is lambda over A, equals m times lambda. And everything cancels out here except m equals 1. So this that I've circled in orange is the m equals 1, or the m equals minus 1, dark spot. So the next one over that I'm circling in green, this would be the m equals 2 dark spot. And then further over in blue, this is the m equals 3 dark spots. But all of these refer to the dark spots, not to any of the bright spots. So let's do an example here. Let's say 550 nanometer light is incident on a single slit, and the second dark spot is at 45 degrees. So the first question we want to answer is, what is the width of this slit here? So we're dealing with dark spots from a single slit interference pattern. So we're going to be using the equation a sine of theta equals m times lambda. We have information about the second dark spot, so we're going to be using m equals 2 here, and theta 2 is 45 degrees. And we know our wavelength, so we can now plug in. We have a times the sine of 45 degrees equals our m value, which is 2, times our wavelength, which is 550 nanometers, or times 10 to the negative 9th meters. So from here, we can then solve for a and get that the width of our slit must be 1.56 times 10 to the negative 6 meters, also known as 1.56 micrometers. Now we can ask another question. So what angle would there be for our first dark spot? So here, the biggest difference is we're still going to be using a sine theta equals m lambda, because we're still talking about a single slit diffraction setup, and we're still talking about dark spots, which is what this equation refers to. But since we want the first dark spot, we need to use m equals 1. So filling in our equation, now we know a, that 1.56 times 10 to the negative 6th meters, and we don't know theta, so I'll leave this as sine of theta 1. And that equals m, 1 in this case, times lambda, that same 550 times 10 to the negative 9th meters. And from here, we can then solve for theta 1, which gives us an angle of 20.7 degrees. So I want to get a little bit at the concepts and the trends involved in these equations. So I have some sort of clicker question type things to ask you guys right now. So if I increase the wavelength of my light, what happens to not only how many total bright fringes there are on the screen, but also what happens to the spacing of them? So we're talking about a single slit interference pattern here. So we still have a sine of theta equals m lambda. So if we're keeping the same slit width, a is going to stay the same. And we're talking about the number of bright fringes. So we're going to be seeing kind of what's happening to m here. But our wavelength is increasing. And sine of theta, we need to think about what this means. But if we want to know what the maximum number of bright spots we can have, how many total ones we have, then we're going to let theta go all the way up to 90 degrees. So here, sine of theta may as well equal 1. So if the left-hand side of that equation is going to stay constant, as lambda goes up, that means m has to go down. So for the same angle, we will have a smaller numbered m. So maybe at 45 degrees before, we had our 10th bright spot. But now at 45 degrees with a bigger wavelength, we might have our 6th bright spot. So the number of bright fringes on the screen will decrease. And if we have a screen that's the same distance away and we want to know the spacing of those bright fringes, well, we have the same size screen and we have fewer bright fringes on it. So the bright fringes must be further apart. So the spacing between them has increased. Now what if I asked you the same question, but instead of increasing the wavelength, I am going to increase the slit width instead. So if I increase A, same question. So now, if A is increasing, and we're going to again kind of assume sine of theta just equals 1 to figure out how many total possible fringes could fit on our screen. And this time we're going to hold the wavelength constant. So as our slit width goes up, that means M also has to go up. So that means the number of fringes we show on the screen will increase. And as before, we can kind of see a slight inverse relationship between this and the spacing between the fringes. We have not moved the screen. So if there are more fringes on the same screen, then there must be less distance between the fringes. Only one other kind of clicker question here. What if we leave everything the same and we just increased big D? We increased the distance of the screen from us. We moved the screen further away. Well, it will turn out that the number of bright fringes isn't really going to change. Because if we have one bright fringe here, and then another bright fringe here, and then another bright fringe here, and here, and here, if we put the screen here, we'll get 5 of them. If we put the screen here, we'll still get 5 of them. So any light that would hit a screen 1 meter away could also hit a screen 2 meters away. The screen just might need to be bigger. So the number of fringes, bright fringes that we show on our screen will stay the same. But as you can see from this diagram down here, as we move the screen further and further over, 2 adjacent slits get further and further apart, so the spacing between the fringes will increase. I recommend asking yourself similar types of questions about the double-slit interference pattern. I think it's a little easier to think about this in terms of the double-slit interference pattern because you can imagine dragging those 2 sources of waves either further apart from each other or closer together, and then you could imagine the effect of changing the wavelength by looking at that path length difference, d sine theta. For some specific angle, you'll get a specific path length difference that's equal to d sine theta. But how many wavelengths is that? Is that 1 wavelength, 2 wavelengths, 3 wavelengths? That'll depend on the wavelength of light, and that will make a difference in terms of how many bright spots you get on your screen. So that's all I have for you today. The first thing we're going to talk about next time is the double-slit and single-slit patterns superimposed into one to get that pattern of red dots I showed you in the image at the very beginning of today's lecture. But we'll get to that on Friday, which should be a fairly short day for our last day of new lecture material. That's everything I have for you all today. Thank you for watching, and have a good day.